Yeah, so let's recap current state of Ethereum. A few months ago, Justin Drake and the Ethereum Foundation post some blog posts, and they introduced the Lean Ethereum, as you may know. The concept is very, very simple and minimize the assumption to, how can I say, very compact verifiability and make post-quantum migration for current consensus layer, not only for consensus, but also execution layers and data availability layers. So today I'm talking about this part, the consensus and cryptography part. So this is a current state of consensus, very sketchy. So at first, someone validator proposed a block, and chosen validators sign for the block, which is a proposed one. And okay, this block state is something that looks good, and aggregator get each signatures aggregator batch into one signature and state and public key and post it to the validators, all validators. And they verify just one signatures. And if the verification is accepted, the block will be introduced to next block. Okay, the problem is, each community have 3,000 validators. So we need to give an efficient aggregation algorithm. And also, the number of validators who verifies one signature is around 1 million. So we need very, very efficient aggregation schemes, and also need a small verification cost. Currently, we have a BS signature, which has a homomorphism, so very, very easy to aggregate and very efficient. Well, sorry, but their signature don't have post-quantum residencies, so we need alternatives. And the Research Foundation currently researching about some post-quantum alternatives, but hash-based signature is top options. Okay, so what is a hash-based one? So as I mentioned before, on top of the ring consensus, we need a very simple assumption. And also, this is a just hash function-based one. We can easily aggregate any compared to any other candidates. Also, lattice-based one is still under analysis, but it is very difficult to aggregate. So here is a hash-based signatures history. And we have a bunch of options, but at this time, we were talking about the XMSS. So this XMSS is categorized to match time signature. I don't know how to say incorrect, but which means in general, any other signature scheme is just one time. But this XMSS has a setup phrase to how much we can sign for future. Also, this XMSS is categorized as a stateful signature. So stateful is not normal, but which has a kind of okay, this signature is not coincide with these messages, or this signature is how to say already used it. We can easy to find this property. So this stateful and match time so XMSS is easy to integrate with current Ethereum POS consensus, because we should watch which slot's signature is okay, this signature has used at t-1, but this signature has not used by t, current t. We can easily recognize that each signature has used this. Okay, so let's move on to the XMSS, how it works. Before we move on to the main topic, let's recap. Okay, so at first, we need a key generation phase, generate a secret key, and the public key is depend on the secret key. After that, we have a message, so encoding it, and so we are here. And index into the signatures. And the signer send each public keys and message to the verifier. And verifier just check which this message is signed by private key. So before we move on to the XMSS, we want to talking about WOTS. OTS means one-time signatures. So XMSS is using the WOTS plus as a building block. Yeah, here is a pro or WOTS plus. Of course, key generation. Yeah. So we have random numbers here as a secret key and a hash for each layers. Hash and hash, hash, hash. And we had 7, 82, 75, 31, and 66. So after we got some numbers, the type of numbers, we can combine each numbers and get into the hash functions, and we got 99 as a public key. So here is what signature setup is do. And after that, we move on to the signature generation step. Here is a message, a word, and encoding. Yeah, here is also random number. And encode it to this tuple of numbers, 3, 1, 2, 1, 2. And this represents how much we should run the hash function. So on the left side, 3, so we can make hash function to move on to the layer 3 here. And here is 1, so move on to the layer 1, 2, and so 2. And after the, yeah, so after the hash, run the hash function for each layers, we got a signature that represents this tuple. And after transfer each messages and signature to verifier, the verifier is easy to check each public key and next signature is verifiable. Yeah, so this is a building block of XMSS. The difference between WOTS is we integrate with a macro tree. So here is already I mentioned. So skip. Oh, sorry. Yeah, here is a key generation step. But this public key represents a leaf of macro tree. So we can generate as a leaf as well as this key generation step. Yeah. So here is just 4 leaves. And yeah, we can get a macro root. And this next step is signatures, and as well as WOTS, get a signature. Sorry, the verification step is a little bit different from WOTS, but very simple, which using the just macro root. So we can just check the macro root is generated publicly. This is the verification step for XMSS. Okay, so this is just XMS. We need an aggregate to, make build blocks. So BLS is a very, very efficient, but they are not quantum resonance property. However, XMSS is a quantum resonance, but not efficient for aggregation. Here is a signature size, current state of Ethereum, it's 96 bytes. However, XMSS one signature has 2.6 kilobytes currently. And also, I assume that current state of consensus layer, we need a height, 31 height macro tree for each year. Yeah, but we have a GK snack. This is, I think, this is a good effect of the programmable cryptography. So we can verify. We can prove that this XMS signature is verifiable. So we can prove that each XMS verification and aggregate check each verification steps, and finally aggregate the proofs, and then just validate verify the one proof. Currently, candidates of pq-sig is pq-sig with real or Ethereum Foundation already use building the minimum GKVM. Here is the aggregation overview. So the validator generates XMSS signatures, and the signature is sent to the aggregator here. The aggregator generates the GK proof that represents verifying the signature validities. And finally, the aggregator combines new proof with existing ones for it. However, this is very, very sketchy, and currently the aggregation method is underdetermined. So here is a recently achieved goal. This slide is from Justin Drake's talk. The important part is aggregate size, which is 128 kilobytes. And verification time, signing time is 100 US. This goal is set as a current spec of the consensus layer. So if we cannot achieve this goal, it might be we need to reduce validator, or we should also consider about 3SF and any other new specs, I think. Here is a GKVM stack. We can use a very, very small field, which is called koala bear. And we just using the hash function as an assumption, so we can use a Poseidon tool for ZK friendly. And yeah, XMS is, and here is a snap aggregation part. So this ZKVM has own custom ISR, and ring aggregation is also custom. So here is, as I mentioned before, not determined. More detail. Yeah, gotcha. Sorry. So here is what we do. Here is my current repository, pull request, and I, how can I say? Yeah, I just improved the signing time and verification time, and we have also benchmarking. Also, we're gonna be into the PQ Interlab on Cambridge next month. We are talking about the unresolved issues and building fundamental for future collaboration with Justin Drake or any other guys. Yeah, sorry. Thank you.
Thank you. Any questions on this? Charlie, do you have any comments on this?
No, I think it's very good and valuable work. No, and it's like to me, using like Stark aggregation for over hash-based signatures does just feel like the only obvious long-run solution. And I even think it has other benefits over BLS aggregation, but I would support it even if quantum computers were never an issue. Like the big one is that you can combine together aggregates even if they already share some number of signatures, which you can't do with BLS, which like actually just makes efficient aggregation much easier in a lot of ways. So that's very, very important technology.
Thanks. We have another question. All right. Thank you. Actually, presentation. So you said it took 0.5 hours to set up one signature.
Yeah.
So this means we have to change the key every year.
Yeah. So the point,
or you can go for 2.5 hours every 5 years.
Yeah. The point is how we can reduce the times of the hash function. So if the height is so very big, we should make many times run the hash function. So we can. It is possible to reduce the height as possible.
What is the height that you're using right now?
Height means just macro tree height.
Right, but do you know what number?
I think the current GKVM has 32.
Okay.
Yeah.
So for 32, so that means your width, right? So that's 5 bits for each one. So the width that has to be about 51, I guess. So that's like still a lot of hashes, right? Like if like optimizing it for data bandwidth and optimizing it for Stark proving are different, right?
Yeah.
So like for data bandwidth, you want like smaller width, but then for data bandwidth you need, but for Stark proving you need fewer hashes. So maybe it's like just a good idea to like put more into width just for that.
I see.
Yeah, it's like on average, right, you'd have to verify the like 750 hashes, right? And then with just like a regular Merkle-Lamport signature, like it blows up a lot. It goes down to like 128, right? So, yeah, so like something in the middle.
Thank you. So I have another question. So if we use Poseidon or something, so we have to fix the scheme of hash function height to use this hash-based signature.
Yeah, for efficiency, yeah.
Yeah. So
We can use SHA-2 or any other hash functions, but we choose Poseidon as for just ZK friendly.
Then so in that case we can use only like Poseidon to friendly with ZK scheme. So like for example.
Yeah, makes sense. Yeah, that's it.
So I think the problem of hash-based signature is like make limit on the ZKB scheme.
I think so. Yeah. So the performance of the ZKVM is depend on the hash function, right? What you mean that?
Yes.
Yeah.
Okay. Any other questions? So maybe like you already have the same question, but yeah. So in this project, that Poseidon 2 is used for any of the hash function. It is like a hash-based signature and then ZK, like a ZK scheme.
So for ZK scheme, and currently we are also benchmarking with a SHA-2 or any other functions as well.
So like one concern is that like as you say, like a lot of space cryptography
Ah.
still under analysis, but I just feel like a procedure tool is like yeah, I'm not sure with the procedure tool is like more like secure than like another.
Yeah. So we need verify by mathematical power. So our coworker also focus on the formal verification to sorry, not only for hash function, but also we have very small assumptions, but which means that we should verify the security by mathematics.
Yes. Yeah. Thank you.
Sorry.
Okay, thank you. Well, let's wrap up this session. Yeah, thank